Today on the show, we're diving into three papers that push AI in very different directions. First, Glint Lab's LLaVA-OneVision-2 rethinks video understanding with codec-stream tokenization, aiming for next-generation perceptual intelligence. Then we head to Fudan University, Imperial College London, Harvard Medical School, the University of Cambridge, and Medtronic, where ECGCLIP learns to read heart signals alongside clinician reports. Finally, from Mila and Meta FAIR, PGT uses procedurally generated tasks to sharpen spatial reasoning in multimodal models. Let's explore the first paper, LLaVA-OneVision-2 towards next-generation perceptual intelligence. LLaVA-OneVision-2 from Glint Lab, AIM for Health Lab, and MVP Lab is a new open vision language model that pushes the LLaVA-OneVision line toward next-generation perceptual intelligence by replacing frame-centric video input with codec-stream tokenization. Built on the OneVision encoder and a Qwen3 8B decoder, it treats compressed video as a continuous bit cost stream. Adaptive GOP boundaries are set from prediction bit cost, and motion residual cues select salient 2x2 patch blocks into compact visual canvases, all aligned by shared 3D rope and windowed attention. Trained in 4 stages on roughly 8 million recaptioned video samples, plus a 4 million sample spatial corpus, it preserves image and document capability while improving event-level video reasoning. The model introduces jump score, a benchmark for dense repeated motion, where LLaVA-OneVision-2 8B reaches 74.9 map versus 30.1 for Qwen3 VL 8B A plus 44, 8-point gain. Across 18 video tasks, it improves the average score by 4.3 points, across 11 spatial tasks by 5.3 points, and on 4 tracking benchmarks by 15.6 average J and F. A controlled ablation shows codec-stream inputs outperform uniform frame sampling by 9.7 points on temporal grounding and by 17.3 points on jump score, while remaining competitive on long video QA. The paper's main claim is that perceptual token allocation should follow coding structure, not elapsed time, and it releases code, data, and model weights as open source resources. Let's explore the second paper, Microsoft Word ECGCLIP Monscript 202-605-12 docx. Researchers from Fudan University, Imperial College London, Harvard Medical School, the University of Cambridge, and Medtronic developed ECGCLIP, a signal language foundation model for cardiovascular assessment that aligns raw 8-lead ECG waveforms with clinician-authored diagnostic reports using clip-style contrastive learning. Pre-trained on 2,837,962 ECG text pairs from 1,324,856 patients, and validated on 9 external cohorts spanning about 1.5 million ECGs, the model was evaluated across 89 tasks, 45 ECG diagnoses, 39 echocardiographic phenotypes, and 5 rare diseases. ECGCLIP R34 was the strongest variant, improving PRAUC over the Merle R18 baseline on the internal Zhongshan test set from 0.37 to 0.409 for ECG tasks, and from 0.273 to 0.292 for echo tasks, while rare disease PROC rose from 0.011 to 0.045. On atrial fibrillation, it reached PRAUC 0.9, on ventricular premature beats 0.913, and on STEMI 0.383, roughly doubling baseline performance for infarction detection. It also enabled opportunistic screening of structural disease from ECG alone, including cardiac amyloidosis with PRAUC 0.201 versus 0.049 for Merle R18, and Epstein anomaly with PRAUC 0.253 versus near zero baselines. A key finding is data efficiency. ECGCLIP R34 matched or exceeded fully trained baselines using only 10% of downstream data. Integrated gradients and t-SNE show that the model learned clinically coherent morphology, such as ST elevation, flutter waves, bundle branch block patterns, and P and T wave abnormalities linked to amyloidosis. Let's explore the third paper, PGT procedurally generated tasks for improving visual grounding in MLLM. PGT, short for procedurally generated tasks, is a data-centric method from Mila, Université de Montréal, and Meta FAIR that improves visual grounding in multimodal large language models by overlaying unambiguous geometric primitives onto training images and turning them into dense, verifiable supervision signals. The paper targets 3 failure modes in MLLMs: spatial relations, abstract counting, and relative distance or depth reasoning. Instead of adding human annotations or changing model architecture, PGT procedurally generates questions about colored boxes, circles, and labeled points directly on existing datasets such as LLaVA, Instruct, 1, 5, and Cambrian, 7M, preserving the original semantic content while forcing the model to attend to image geometry rather than language priors. Across 4 backbones in instruction tuning, Vicuna, 1, 57B, Llama, 38B, Quen, 2, 57B, and Quen, 2. 514B, PGT, raises what's up by up to 20 points, and CV Bench, 2D, by up to 13.3 points, with consistent gains on CV Bench, 3D, Blink, and TallyQA, and little or no regression on general benchmarks like GQA, POPE, and MM*. When fine-tuning state-of-the-art models such as Quen, 2, 5VL, and InternVL3 with only 5K PGT samples, the method still improves spatial and depth benchmarks, sometimes outperforming specialized real data mixes and RL-based baselines like Vigo RL and Spatial Ladder. Ablations show that removing the relative distance task sharply degrades 3D depth performance, indicating that 2D geometric comparison may be the core transferable primitive behind emergent depth understanding. That's a wrap on today's AI paper highlights. Thanks for watching.